I'm going to give you a Reader's Digest version, or maybe I should say a bumper sticker version of my first year learning spectroscopy with the Shelyak LISA spectrograph. First I'm going to say that Photoshop made me do it. I started out deep sky imaging and found it to be very frustrating trying to take the light pollution out of my images from Phoenix suburb, all the ambient light, and just wasting a lot of time. So I started thinking about maybe I could do science with my small telescope, and I was talking to my good friend Mr. Moon, which many of you may know, and he said, Woody, maybe you ought to come to SAS and see what's going on there. And he said, you might want to look at spectroscopy, although it might be a little bit hard. So I bought some books on spectroscopy and thought I'd give it a go. So I bought where's my advancer? So that star that you see there in the center looks a lot more interesting when you put a grating or a prism or something in front of it and unpack the data in that little white dot. You see quite a bit more information. You can see some lumps in that line there at the bottom, some emission lines in the visible range of the spectrum. And I thought that looks pretty cool. This is already looking interesting. Figure out which way this goes. So I bought a SA200 diffraction grating and put it on my C11 with a color camera. I didn't know at that time that monochrome would be better. And I thought it was a pretty cool image. This is a beveled grating, glazed grating, I'll get it right. And so this grating allows most of the light to come through for the zero order, that center point of each of those stars that you see. And you'll see, because it is blazed, you'll see much of the energy in the first order will be on one side of the central star and less energy on the other side. And I have this oriented with the stronger first order signal on the right-hand side of the image.
This was 5/62 unguided images with C11. So there's a lot of information there, a lot of stars to study. So this is quite promising. The star in the center is Wolf-Rayet star, Wolf-Rayet 155. And these stars are very interesting. They typically have highly ionized helium and nitrogen or carbon in them. And surface temperatures 30,000 to maybe 200,000 Kelvin. So again, this is looking more interesting. This is a profile by Olivier Tizzy in France of that star. And you'll see two of those very bright emission lines in this profile. It's my understanding you can't talk about spectroscopy without an HR diagram, and I saw that John Bally had an HR diagram, and I thought, well, if one's good, four's better. What these diagrams have in common, for the most part, is they have a luminosity scale that increases on the y-axis and a temperature scale that typically increases to the left, except that one in the lower left corner is backwards. You'll see the main sequence of stars there from the upper left, most massive blue-colored hot stars down to cool M stars down in the lower right. And you'll see some other interesting groupings there of red giants, supergiants, and white dwarf stars. And I've become particularly interested with the equipment I have in symbiotic stars, and they combine a combination typically of a red giant star and a white dwarf star. So I get to look at something that combines two different places on this HR diagram. The upper right diagram is pretty interesting. There's a theoretical prediction of where our sun will go through this HR diagram, becoming a red giant and eventually going around past Rigel, or where Rigel is now, and all the way down to becoming a white dwarf. So these diagrams, Hertzsprung-Russell diagrams, have been in use for a little over 100 years and are very useful for star classification and studying stellar evolution. So, what do you need to get going doing spectroscopy? A telescope and spectrograph. I'll come to that a little bit more in a minute. I started with a C8 on a CGEM mount in my garden.
You'll look carefully, you'll see on the back of that something looks almost as big as a telescope. Is a Shelyak Lisa spectrograph. This is an R1000, resolution 1000, so at 6,000 angstroms, my resolution is on the order of 6 angstroms. It has a science camera. You'll see it's an ATIC 414 in the lower left side, a very low noise CCD camera, and I have a Lodestar X2 guide camera. What's nice about this instrument is it comes with a guiding module, and you'll see that white box there is a calibration module that has a built-in tungsten lamp for flats and a built-in neon argon lamp for shooting wavelength calibration type frames. This was a great configuration for getting started, and people do a lot of good science with this configuration, but I wanted to deal with this problem of having to take it down at night and then set up the next night with alignment, polar alignment, and all that stuff. So I moved it into my observatory. I put it on a C11 and on an astrophysics mount, and this made a number of improvements, one being much less time spent finding my targets, and gave me a little bit more depth in terms of going after dimmer stars, and guiding was better, just obviously a better installation. The downside to this configuration, I found out after using it in Phoenix, the temperatures can drop very rapidly when the Death Star goes down in the evening, and I was spending a lot of time refocusing. And with the mirror flop and this kind of design, sometimes I was only going 20, 30 minutes and I was out of focus. So I started thinking about a way to solve that. I tried temperature compensating focusers, several different solutions, and they work a little bit, or at least for me, I got them to work a little bit. But I started dreaming of something with carbon fiber, and I think all of our sponsors will be pleased because I've got some of everything from our sponsors here. But the PlaneWave CDK was solved so many problems. Focus is a non-issue. I've checked focus, but I've only actually made 2 focus changes, and they were very small this whole last season. And with no mirror flop, I can put a target 99% of the time on a 6x8 arc minute field of view on the guide camera, which is how I find the things that I'm looking for. So you have all this equipment. now you need to make more friends to help you understand how to make it actually do something. And I've been very fortunate that David Boyd and Paul Lucas, that many of you know in the lower left picture there, have been very helpful in answering my questions and tutoring me along. On the right is Francois Tessier. He's kind of a de facto head of the French amateur spectroscopy group of people, and we had the pleasure of staying with him at home in France
last year, and been extremely helpful and motivating in getting started in this sport. And some of you may recognize that guy in the center, Wayne Green. All these people have been just tremendous in helping me move forward along this path. So you have to choose a target and a suitable reference star. The reference star, in a way, is more important than the target star sometimes. But I've been interested in symbiotics, novae, and supernovae, and these are particularly appropriate for a full visible spectrum R1000 spectrograph. I use the Miles secondary reference stars. You've probably heard of Pickles stars, and I'm sure there are many others that I'll learn about after I'm done speaking here, when people come up to tell me, did you know about? But these Miles reference stars are very good for what I'm doing. They're around 3,500 to 7,500 angstroms at about a 2.5 angstrom resolution. And they're very carefully measured on the Isaac Newton telescope, is my understanding. And so they make a very good reference star for calibrating my instrument and my atmospheric conditions, such that when I produce a profile, it's comparable to that created by people with other instruments in other places. Typical data set for a Lisa spectrograph, bias frames, same concept that we'd have for deep sky imaging. I do these in advance. Darks, I scale
the darks because most of my images are somewhere in the 30-second to 300-second with some 600-second images. The reference stars, I try to choose Miles reference stars that are in the magnitude 5, magnitude 6 range, so they don't take a lot of time. So those are typically 30 seconds and give me a good signal to noise ratio. I also take, obviously, the light frames for the targets, and if it's a symbiotic like CH Cygni, that might be 30-second images. If it's like T Corona Borealis, I'll take a set of 300-second images, and some of the novae and supernovae that I've gone after as follow-up have been 600-second images. I use that tungsten lamp in the calibration module to take the flat frames, and the neon argon lamp in the calibration module for these neon argon images. I take one of these immediately before the target or the data on the light frames on the reference star, and again immediately before the target star. So I'll slew to the reference star. I'll take a calibration image with the star pretty much on the center of the slot, of the slit at that point. And then again to the target star, take a reference or a neon argon image there. And then if the target star is of any significant duration, 20, 30, 40 minutes, I'll also take a neon argon calibration frame afterwards to see if there's been any shift in my instrument. And it's important that all these are acquired at the same temperature. For spectrum processing, I'm primarily using ISIS. Poor acronym. I've looked it up 3 times, and each time I forget. Spectroscopy is one of those S's. It obviously is able to use those bias darks and flats to calibrate the light frames. And the magic sauce in this whole process in the software is this guy, background subtraction. ISIS does a very good job of that, and I'll show you another slide in a minute on that. But that's what allows me to actually do science in a very light polluted Phoenix suburb. And then it takes these neon argon frames that I mentioned for the reference and target star and allows me to calibrate, wavelength calibrate that all those pixel locations across that CCD, and I'll show a quick screenshot of that here. And then we work on this response profile curve. This is what I'd mentioned where we correct for the instrument and atmospheric conditions by taking a spectrum of this reference star and correcting it such that it matches the profile of the Miles star, and then we can take that same correction and apply it to our target star. I use Plot Spectra by Tim Lester. I should have mentioned that ISIS is Christian Buell, a French guy, and Plot Spectra, Tim Lester in Canada, and it's very helpful for plotting and identifying absorption and emission features in the spectrum, and you can do some analysis, which I'm beginning to learn, like calculating equivalent widths and radial velocities. This is one of just a couple screenshots I'll show you. There's a spectrum here of T Corona Borealis, and what I want to draw your attention to here, those blue lines are the binning zone, or the area that I'll include that signal as counting towards the spectra. It also allows me to calculate the tilt, and the software will adjust for any misalignment that I have in lining up that spectrum on my x-axis of my CCD camera. And here's the light pollution. I probably could have stretched this more and shown you how bad that really is, but you'll probably see quite a few vertical lines running there. Those are the length of my slit, and that's car dealerships and street lights and all the wonderful things. I skipped over the sky background subtraction zones. Those are the guys there that I can define the size of those and move those around in case there's something that a cosmic ray hit or something in there. But those allow me to take that background light pollution out of my spectrum data. This is an image of the neon argon
calibration frame. I've identified here the 5945 angstrom line at pixel 871, and that with a spectral calibration file that I have in a subfolder that identifies the wavelengths of the neon and argon emissions in my
lamp, it can fully wavelength calibrate that spectrum. So here the blue line is my spectrum, the red line is the Miles spectrum, and that green line is the correction that ISIS has calculated that would allow me to convert mine to adjust for, again, the instrument and atmospheric conditions. We actually smooth that green line a little bit before we apply it, but if you've done everything right, the red line is the Miles line, and it overlays my corrected profile, the blue line, very nicely. So that's, now I can apply that with some confidence to my target star. So here is T Corona Borealis displayed in plot spectra. You can see a number of annotated emission lines there. This was 8 300-second stacked images with a resolution just over 1,000. This is a symbiotic variable star. So there's this white dwarf in an orbit with a typically white dwarf. You see an accretion disk there and maybe a little bit of gas flowing from that red giant through the Roche lobe into that accretion disk. The continuum feature here, you see these sort of ramps, and these absorption drop-offs are attributable to titanium oxide in molecular form at these cooler temperatures. And so we've really got the spectrum of two stars overlaid here, where part of it is clearly M3 type spectra, but all these emission features are probably coming from that accretion disk, the white dwarf, or maybe the nebula gases that surround all of this. And that's year 2 stuff for me, is to begin to figure out what those things are. Okay, we've made it, except for one thing. We've got to get down safely. Oh, no, wait a minute, that's a different thing. Our data is much more valuable when we share it with others, so I share my data with the ARAS spectral database maintained by Francois Tessier. He is a good conduit to professional astronomers and a good reputation for the quality of this data. I also share it with the British Astronomy Association, who has a database maintained by Andy Wilson. Both of these allow you to download FITS files to compare with your data. And if you get really lucky, you get your name on an astronomer's telegram for some of the data that you've worked so hard to get, and that's kind of a nice bonus for many, many hours. So thank you for your attention.